In the last video, we saw that the fact that all observers agree on the same speed of light requires us to revisit our assumptions about simultaneity and how different observers are experiencing distance and time. To wit, we saw that moving meter sticks are short. It looks short to someone who sees them as moving, and moving clocks looks like they're running slow to someone who sees them as moving. Now, in that video, I pointed out that if I walk past you and you look at my watch, and we both happen to have atomic clock watches and we were watching super carefully, you would notice that my watch was running a little slow compared to yours. And I would say that since I'm entitled to be an observer and say that I'm stationary and you're the one moving, I'd say, no, it's your clock that's running slow. So this gets us into a bit of a pickle that gets called the twins paradox. And so we need to think about how to resolve it. So in the twins paradox, what we imagine is that there are two twins who we will cleverly call O and O prime. Initially, they were both going to be going on the same spaceship heading out to some star 10 light years away. A light year, by the way, is literally the distance that light travels in 1 year. So it is the speed of light times 1 year, or 3 times 10 to the 8 meters. Or we can say that this is 3 times 10 to the 8 meters per second, roughly, times a year is roughly pi times 10 to the 7 seconds. It's not exactly that, but it's close enough. So anyway, you get something just a bit shy of 10 to the 16 meters. But what's really handy is that you can then say the speed of light is 1 light year per year. So that's when dealing with astronomical travel, that is a very handy unit. So anyway, our twins were both going to go on the same expedition out to this star over here. And they would be going in a spaceship that could travel at 0.9 times the speed of light. Now, shortly before the launch window, one of the twins broke their leg in a skiing accident, and they weren't permitted to join on. Someone else did in their place. But what that means now is that the twins are separated. One is going to remain on Earth while the other one travels back and forth to the distant star. Now, it turns out that perhaps the twin that got to stay behind on Earth, that things actually worked out okay for them. Because what wound up happening is that the spaceship traveled out to the distant star, and then it turned out that the inhabitants of that distant star made it abundantly clear that they didn't want any visitors. And so the starship just had to immediately turn around and go back home without even landing or anything. So that was a lot of time in the starship. So let's start to figure out how long, in fact, this is going to take. Well, for O here, O is going to say that this round trip was 20 light years, or that each leg of the trip, let's call this leg 1 and leg 2, would take 11.1 years to do, because 10 light years over 0.9 c, that's going to work out to be 11.1 years. So the dilated time for leg 1 is 11.1 years, and this is because the spaceship is seen as moving. And similarly, the dilated time for leg 2 is also going to be 11.1 years. So, back here on Earth, they just said, hey, out 10 light years at 0.9 light years per year, 11.1 years out, 11.1 years back. So, definitely aged 22.2 years. Now let's go and think about this from the perspective of O prime, our twin who actually did go on the rocket journey. First off, if you do the length contraction calculation, what you will get is that O prime is going to say that the distance between the stars, because remember, the twin on the rocket ship is going to say the sun is moving away from them and the star is moving toward them on the way out, then on the way back the other way around. But either way, that twin, when you do the relativistic, when you do the length contraction calculation, that twin is going to say that there are 4.37 light years between the sun and that distant star. Now, that twin is going to be measuring the proper time that it takes, because first the twin will see the sun where the twin was at, and then the distant star. Since it's the same location, that's a proper time interval. Well, we can work out that proper time interval. 4.37 light years divided by the speed of light, 0.9 light years per year. That is going to take 4.85 years. And same for the return journey. The twin is going to say that took 4.85 years for this star to move away and for the sun to get back to that twin. So if we add that together, we get that O prime aged 9.7 years. So 12 and a half years different, quite a bit. So what's going on here? Couldn't we say that, but wait, you swore to me that O could say they're stationary and that O prime is the one moving and that O prime's clock should be running slow. So then wouldn't we say that, since definitely O prime is convinced that they age 9.7 years, wouldn't they be convinced that their twin left behind on Earth aged even less than 9.7 years and then back and forth? So we have to break that paradox here. And so it turns out that one of the key assumptions of special relativity is that you are an inertial observer. That means that you are not accelerating. Now, one of these twins is inertial and one of them is not. Which twin is not inertial? Pause the video and get back with me. Okay, so O prime is not an inertial observer. At points A, B, and C, the twin had to accelerate. First to go from 0 to 0.9 C to the right, then to reverse course to go to 0.9 C to the left, and then finally to come again to a halt to meet up with their twin back on Earth. That's enough to break the symmetry, just the fact that these 3 accelerations happened. And that's enough to say that now O prime was definitely the one that aged less. But, you might say, surely we could imagine that the rocket got up to 0.9c very quickly, so quickly that over 4.3, over 4.5 or 5 years or whatever, that amount of time basically didn't matter worth a hill of beans. Okay, I'll go ahead and grant you that. But then the thing is that O prime was first moving to the right at 0.9c, and then they were moving to the left at 0.9c. So they actually occupied two different reference frames during the journey. And that's also enough to break the symmetry. In fact, a calculation that you can do is to just say, let's imagine that O sent out a birthday message by radio every year to their twin on O prime. So on the way out, the birthday messages will be sent once a year, and they would be traveling at 1 light year per year. Now to O prime here, they would say, okay, that's all well and good. But then that means the second message, O was a light year, was 0.9 light years further away from them. So when you figure out the fact that O prime says that O is running away from them, and so that each subsequent birthday message takes longer to get to them, you would figure out that on the outbound trip, if we do fractional birthday messages, O prime would receive 1.115 birthday messages. Now, O prime would say that O was turning around, but now O is sending messages, is catching up to their messages. They're traveling toward O once at 0.9c, so they're only getting a little behind their birthday messages. So when you work it out, what you get is that in that interval, they'd receive 21.188 messages. Added up, it works out to be 22.2 years. So that's how we resolve the twins paradox. You can only do meaningful comparisons of time when two things are in the same reference frame. O was first in the frame of the Earth, then in this frame to the right, then this frame to the left, and then back to the Earth. By jumping all the frames, O prime did that. So by jumping all the frames, it meant that O prime was the one that aged less.